So good morning, everyone. I'm Florian Brouillet from University of St. Andrews, and today I will present you a part of my PhD. So our new insight on the Laki eruption and its plume evolution, with from sulfur isotopes from high time resolution ice core. So the Laki eruption was a huge visual eruption which occurred in Iceland from 8th of June 1783 to 7th of February 1784. It was composed of 10 major phases, which are represented on this diagram. It released 100 megatons of sulfate, which after was precipitated as 200 megatons of H2S4. And this huge amount of sulfate was released really at the beginning of the eruption. So 80% of the total sulfate were released at the end of the 6th phase, so just 2 months after the beginning. And for example, if a Laki type eruption will occur at present time at the same place with the same amount of sulfate eruption, we will have an excess of mortality of 142,000 in Europe in the years following. So following this eruption, a strange climate appeared. So at first there was like a dry fog which appeared in Western Europe from late June to end of October 1783. It was like a thick fog, difficulty to see through some days smelling sulfur. But the more interesting is the temperature. So the summer following the eruption, so the 1783 summer that we have here on the first diagram, we see a small peak of excess of temperature, a little bit hotter than normal. But the most important are the winter. So the winter following the 84, 85, and 86, which are represented here on the second diagram just here. We see very colder than normal. So we have the 83, the one before the Laki, was quite normal at 0. Where we have the 84, the one following the eruption, was 3 to 4 degrees colder than normal. And it took like 5 years to come back to normal. So as volcanologists, we can ask ourselves, yeah, did the Laki impact the climate? So the best to investigate that is to look at the real age of the plume, so at which altitude the sulfur was injected into the atmosphere. So for that, the best is to look at the sulfur isotopes, especially in ice core. Why the sulfur isotopes? Because if a sulfur is injected at high altitude, that significates above the tropopause and reach the ozone concentration. So we have here a representation. It will result photochemical reaction of the sulfur, which will give to the sulfur a cap delta 33 non-equal to 0. We call it mass independent fractionation, a MIF signal, because normally a volcanic eruption have as a signature of cap delta 33 of 0. So for example, here is a typical stratospheric eruption, which was recorded in ice core. We have on the top the sulfur concentration, so we have a nice peak. On the second diagram, we have here, so the cap delta 33. The first things that we see is the cap delta 33 for all the samples are not equal to 0. So we have a MIF signal on the whole record. Also, we have an evolution, so from a positive to a negative peak, so a nice pattern. But the most important here signal is we have a coupling, a correlation between the cap delta 33 and the delta 34 sulfur. They follow the same pattern. So now, if we can record stratospheric eruption, do the Laki record show a measurable stratospheric component? So some scientists try in 2012, and they say there's no evidence of stratospheric sulfate in the Laki. So they took 3 large samples in Greenland ice core, so the ice core summit, and I report here the result of their analysis. So they state all the cap delta 33 are within error are equal to 0, and also they add that the first samples is slightly negative, where normally for a typical stratospheric eruption we'll expect a positive more than a negative. So for answer to this paper, we can say at first, so here we go back to this sketch where we have the tropopause and the ozone concentration. We see on that part that At high latitude, so between 40 to 80, at low stratosphere, we have a window where we are below the ozone layer. So that significates if the Laki eruption injects some sulfur into the lower stratosphere, that will not generate a MIF signal. So it could be a stratospheric eruption. But in the same time, the same year, another article was released and state that we cannot use mass-independent sulfur isotopic composition measurements on the Greenland ice core for the high latitude eruption due to a fast deposition. And for that, here is a stratospheric eruption from high latitude. So this is the Nova Rupta Katmai from Alaska of 1912, recorded in ice core. So here we go again, we have the sulfur concentration in the ice core. And if we look at the Cap Delta 33, we have some measurable at high resolution MIF signal. So that significates for high latitude, we can have a MIF signal. But where for the stratospheric eruption that we saw before, here we don't have a correlation between the Cap Delta 33 and the Delta 34, because the tropospheric component is released very quickly in the ice core, and because the tropospheric component has a signature of 0, it will mute the MIF signal. So if we can measure stratospheric eruption at high latitude, can we detect stratospheric sulfate from Laki with a high resolution sampling? That's what we made. So we went to Copenhagen Ice Bank, where we measure. We sampled 21 samples from North Greenland, which give us 1 to 2 months per sample's resolution, which is high resolution. And all these samples, we measure it on MCIC PMS Neptune in St. Andrews. So here is our result. So on the bottom, we have the sulfur concentration. We see the nice sulfur concentration peak. Just on above, we have the Delta 34, where we see a nice pattern, a trend from negative to positive, with the two background on the edge. And the most important, the Cap Delta 33 here. So we have the two background here, one samples with high error bar, but after we see we have a negative to positive trend, and after we have a nice plateau, and on this nice plateau, we have a small but measurable non-zero Cap Delta 33. So that significates on this record of the Laki eruption, we have a little bit of stratospheric sulfate. And the negative to positive trend that we had here is slightly similar to the one that Lansky found on the paper, but because to the low resolution, we don't have this nice trend. And if we compare the Cap Delta 33 and the Delta 34, we see the same trend, but there's not very nice correlated. So that significates most of the Cap Delta 33 is muted by a major tropospheric sulfate emission. So what that implies for the Laki eruption itself. So at first, that significates the Laki plume is mainly tropospheric, but with a small stratospheric component, because we have a small but a measurable non-zero Cap Delta 33. So if we report it on this diagram, that significates the Laki plume reach this part of the atmosphere, which is between 10 to 30 kilometers. And that significates it's also consistent with previous volcanological estimation of the plume 8, which was between 8 to 13. So now we can say it reached at least 10 kilometers and can go to 13 or maybe a little bit higher because we have a non-zero Cap Delta 33. So for finishing, because we have here a proof of the Laki injection at stratosphere, that indicates we can have some sulfur which have a residence time a little bit longer than expected, so we could have a potential possible climate forcing of the Laki. Thank you for your attention.